I want to finish up the notes from today that we were not able to get to because of the fire drill. The first thing that we need to talk about is this new idea of congruent figures. We already know that congruent figures are the same shape and size, but our extended book defines them in a new way. It says two figures are congruent if and only if there is an isometry of F such that one of the figures is the F image of the other. All that's saying is if you have two figures the same shape and size, you are able to move one to be right on top of the other by composing several different line reflections. So if there is some isometry, meaning the composite of several different line reflections, that will take a figure and map it to the other one, we can say that the figures are congruent. The next type of transformation I'd like to discuss is called a glide reflection. A glide reflection is an isometry if and only if. Let's start over. An isometry is a glide reflection of the plane pi if and only if there is a line M in pi such that G is equal to a translation composed with a line reflection. The requirement for it to be a glide reflection is that T cannot be the identity mapping and T is parallel to M, meaning that the vector that would move A to B, if this is my translation, the line needs to be parallel to that vector. So I have a picture drawn here of a glide reflection. I started at this triangle HIJ. I first translated it from A to B. You can notice that HIJ moves to H prime, I prime, J prime. It traveled along these parallel lines in for the same distance as A is from B. At that point, I reflected over line M. You'll notice that line M is parallel to the vector AB. So when I reflected, it landed at H double prime, I double prime, J double prime. That is what a glide reflection is. So the questions are there any fixed points of a glide reflection? And the answer is no, there can't be. If I translate, everything is moving and we are not allowing it to be the identity mapping. And it does not preserve circular orientation. It is an odd isometry. So let's go back and look at this a minute. You'll notice first, I'm translating. Translation is the composite of two line reflections. Then I reflect over line M. That is my third line reflection. So while circular orientation is maintained or preserved from the translation, once I do the line reflection, circular orientation is reversed. So it does not preserve circular orientation. And again, it's an odd isometry because I can create it by reflecting over an odd number of lines. The structure of the transformations that we've discussed are pictured here. The first heading is all the mappings of the plane. Okay, a mapping is a function. Under mappings, I have permutations. Remember, permutations are mappings that are both one-to-one and onto. And a subset of permutations are isometries. Those are the mappings that take one figure to congruent figures. Under isometries, I have odd isometries and even isometries. Even isometries are compositions of an even number of reflections. Odd isometry is the composition of an odd number of reflections. Under the even number of reflections, I have rotations and translations. Remember, a rotation is formed by the reflection over two different lines that intersect. A translation is achieved by reflecting over a set of parallel lines. An odd translation, the two that we've seen, are reflection and glide reflection. Remember, odd isometries reverse circular orientation, while even isometries preserve circular orientation. And that is all you missed from the notes today. You are now caught up with first period. So just proceed to do your homework. Have a nice night.